Hey, good afternoon, everyone. Welcome to next session is called correlation between MPC and ruler in laboratory oxidative conditions. My friend and coworker Cristian Soto will be presenting. Take it over, Cristian.
Okay, thank you very much, Greg. So we just went over the title. So the objective of the work presented here is to explore the following orthodoxy, that antioxidants are meant to extend the life of an oil, and therefore antioxidant retention and monitoring is an indication of remaining life. So we're going to put these orthodoxies to a test by monitoring the oxidation using an accelerated oxidation testing equipment, and then monitoring the process using ruler, RPVOT, and TAN, total acid number. And then we'll be looking for correlations between these monitoring tools and the actual formation of deposits, and through monitoring the membrane patch colorimetry, the delta E. So that's we expect that through this type of work, we'll be gaining more insights in relationship to definitions of remaining useful life, condition monitoring strategies, and into the future, the use of sensors and end-of-life decision making. So let's do a little bit of quick background check. Most of you are probably very familiar already, but it's good to revisit this, as it will give us a framework and by which we will be reviewing our results. So oxidation produces harmful effects to the base oils through the formation of reaction products. These reaction products end up impacting the actual physical chemical characteristics of the working lubricant, which then end up impacting performance specifications such as foaming, divulsability, viscosity, and the likelihood of deposit formations that may imperil the smooth operation and reliable operation of the working equipment. So we're going to monitor this degradation through oxidation, as I mentioned, using ruler, RPVOT, and TAN. This time, the focus of FTIR is not a focus of this presentation, although it's worthwhile to mention that it's another powerful tool by which one can monitor the degradation byproducts and consumption of antioxidants. So a little more background here on antioxidants. The purpose of using antioxidants, of course, in formulations, as their name state, they're there to reduce the negative effects of oxidation. And they do this by being sacrificial. In other words, they get preferentially oxidized. That means that they're donating their protons to free radicals that are formed. And in this process, they convert themselves into stable free radicals. And in that process, other species are also generated. The reactivity and solubility of these byproducts are just as crucial as the byproducts of the oxidation of the oil itself, in terms of deposit formation and impacts it may have on things like demulsability and foam, etc. The various parameters by which we monitor how well the lubricant can support a reliably operating piece of equipment. It's very important then, all these implications in terms of antioxidants, because they're really meant to produce a benefit. And simply stating that we have more antioxidant and that in and of itself is a benefit is not really good enough, right? It's a circular argument. So what is important is that the antioxidants do in fact provide a benefit in terms of life extension of the functioning parameters, performance parameters, and that when these are used as tank side additives or as part of feed and bleed programs, they don't actually create more problems than they solve. Although they may have extended they have a larger ruler value or a longer RPVOT. So, and again, just reiterating here what I just stated. So, to be relevant also to take a closer look at the mechanism of oxidation, because later on it will be helpful in terms of explaining some of the data we observe. So here we show the RH is basically a hydrocarbon, basically would be the oil, which under heat and oxygen can generate radicals. At really high temperatures, we can also break some carbon-carbon bonds and create some radicals in that way as well. These radicals then react with oxygen to make some peroxide radicals. And these then attack oil again and produce another radical, and the sequence just can repeat itself. This all can happen at relatively low temperatures. Certainly, in this case, is an example of under 120 degrees. When we talk about using an antioxidant, we're talking about really basically preventing this formation of free radicals following the peroxide radical formation, since it will work with this. It will react with these peroxide radicals, and they're neutralizing the next set of reactions, which are radical formation steps, and lots of free radicals are created. And so that's exactly where the antioxidant is terribly helpful, is with one molecule you can neutralize 4 molecules of radicals at low temperatures, and at high temperatures, depending on the antioxidant, you could be neutralizing 40 plus free radicals depending on the specific reactions taking place. So what's the meaning of this slide in some ways is to show you that oxidation is not simply a simple reaction of A plus oxygen resulting in an oxidative molecule, but it's a reaction that has lots of steps, and it has the possibility to create a number of different compounds that includes aldehyde, ketones, and alcohols at low temperature. And at more elevated temperature, this can result also in the formation of acidic species. This is further just delineated and show the complexity of this process by a slide that maybe many of you may have seen, which shows these propagation reactions as circles, basically, where the free radical comes back, again, interacts with a new molecule of oil, and it can continue to oxidize the oil quite quickly as a chain reaction. We're also highlighting here that the formation of aldehydes, ketones, and alcohols tend to occur at lower temperatures, while then those resulting products can, at higher temperatures, generate more acidic species. And this is just a summary of not the steps of those reactions, but kind of a listing of the various end products that can be formed. And as the temperature increases, and you to the right, you leads to the formation of acidic species. At what exact temperature, that is impacted by things like catalyst. So we, over the years, right, through ASTM, methods have been developed and attempts at establishing, okay, what numbers of these techniques by which we monitor oxidation can be utilized to basically give warnings to the end user of when to take action. ASTM D4378 is kind of the standard on this, and it basically tells us if there are less than 25% total antioxidants left, as measured by ruler, we are approaching end of life. Our PVOT, if we are less than 25% of the original value, we are approaching end of life. And TAN tells us if we more than 0.3 milligrams of KOH increase, one could say that we are approaching end of life as well. And then ASTM 7843 doesn't tell us end of life, but it says you're in a critical condition if your delta E value of membrane patch colorimetry is over 30. So We would like to put this to the test by actually oxidizing material in a control manner and see how these results of these monitoring strategies compare to those of the delta E, MPC, and actually visuals of whether deposits were formed or not, and evaluate whether this guidelines or estimates and recommendations of RPBOT, ruler, and TAN are able to correlate with the formation of color bodies that will be captured through MPC and or deposits on the actual test tubes where these reactions take place. So let's take a look at these experimental results. So the turbine oil performance prediction test is an accelerated oxidation process. Typically, the test is done at 120, but one can change that temperature to explore what's happening, what chemistries occur at different temperatures. The test also includes the use of air, dry air, and an immersed catalyst. So let's start out by taking a look at the total acid number and see what happened when we oxidize this number of different oils, to 15 to be precise, and see how these various oils reacted to this treatment. So here is a collection of 14 of these oils, and we can see that most of them actually did not show acidification at 120 degrees C. The acid number remained basically unchanged. Here for reference, we have the 0.3 milligrams KOH as a scale within these diagrams. Only one of the oils actually showed acidification at 120 degrees. When we ran this test at 180 degrees, but for only 5 days, an entirely different set of results emerge. Here, for reference, we're providing in the blue columns the results of the above, the numbers at 120 degrees after 12 weeks. So we're comparing, we can see that oil number 6 here showed no acidification at 120 degrees after 12 weeks, while oil 6 showed massive amount of acidification at 180 degrees. And so how can this be explained? This is very much indicative that there is entirely different reaction chemistry taking place at 180 than at 120. So we are not really accelerating the reactions that are happening at 120. We are opening possibly entirely different reactions. It's also important to point out that depending on the formulation, your acid number may start with particularly high values to begin with. So something to consider when we're looking at the changes in acidification. All right, so we'll continue. And now we will take a look at MPC. Here what we have is from left to right are the 12 different 14 different oils, and then by using columns, we identify the various weeks of stress. As you can see, when especially we compare against 120 degrees, we were saying, well, not much happened at 120 for most of the oils in terms of acid formation, but in terms of MPC or delta E, we see many oils actually began to show evidence of reaction products occurring. Very important here as we're starting to correlate acid number and MPC and see if these correlations actually, makes sense or exist or not. And so we also see that some of the oils, number 10 and 11 in this example, which are showing critical levels of MPC already at 3 weeks, and certainly then extend into 12 weeks, they remain in critical condition, show no evidence of acidification. And one more thing to point out is the same, using as an example, oils 10 and 11 show a rapid increase on delta E to then fall back down and then increase again. So a number of different interesting results that one can observe by doing this type of testing. But we are basically making a tabulation here of the various series that are showing that are in critical condition. And here, number 5 by 10, and then 9, 10 through 14 due to MPC. So then we're comparing here MPC at 180 degrees C and the highest MPC at 120. And you can see that the lubricants that produce the highest DE at 120 are not necessarily those that produce the most highest numbers DE values at 180. So once again, 180 and 120 are not like one just an acceleration of the other, but rather an entirely different reaction path occurring. Here we can see also that those oils at 180 that produce a lot of DE, they're not necessarily like in the case of oil number 11, significant increases in TAN. And similar here for example 14, where actually we did not see an increase on acidification at all. Well, we have a significant amount of increase in delta E's for both 120 and 180. So again, this can be explained by saying, well, at 180, some very different things are happening than at 120. So now, let's take a look at the next set of data, which is comparing MPC to actual deposits. So once again, here we have the oils organized from 1 to 13, with the number 1 having the lowest MPC and number 13 having the highest. And then taking a look at what the test tubes of the oxidation process look like after 12 weeks. As you can see, there is a fairly good correlation. All those with the highest MPC are also showing the highest amount of deposits, although there are some notable exceptions. For example, number 6, where we do see some deposit formation. And we also see that number 13 is somewhat lighter in deposits than number 10, although the E value of the MPC is higher. So how do we put this together? How do we, it seems very chaotic, but when we look on average, the overall, say, mantra, right, that as the delta E, as the RPVOT go down and the ruler value go down, the MPC value goes up. So that general trend holds. And we can see this by taking the average of all the oils. So here we're mixing lots of different oils, right? I mean, not mixing them physically, but mathematically speaking into an average. And we see that, it makes sense, right? Now, the ruler is more sensitive than RPVOT. That also makes sense. We're probing only antioxidants, while the RPVOT is also looking at all factors, not only antioxidants, which causes the response of RPVT to be a little bit blunted. And we also see that the ruler values tend to start to flatten out. It's also consistent as the concentration of antioxidants getting consumed, the reaction rate slows down. And so you would expect a slowdown in the consumption of the antioxidants themselves. So all this makes a lot of sense, but why do we get all this variation? And the reason that happens is when we look at the individual responses formulations, and we see there's a huge variability. So we see that several formulations reach critical level during ruler, although if you were to average over the response, you wouldn't reach, they don't reach criticality, but there is many of them that do. And these are captured here where at the top of the graph with the critical series, 11, 2, 3, 8, and 5. And in the case of our PVOT, we have several, just number 10. So now we can start comparing things and estimate, right? We can use ruler PVOT 10 and then think about, oh, what would we expect for a high MPC? And when we do that, we see that there is not a very strong predictability by looking at ruler PVT and 10 to determine that end of life, as described by ASTM. And what we do see is that MPC actually does have a good correlation with varnish deposits, with some exceptions. So how do we explain these results? We explain these results by saying, well, there is a lot of complexity, as we saw on the oxidation of the product, with many different types of products forming due to oxidation. In addition to that complexity, we have the mechanism of antioxidants operating themselves, bringing more complexity. So you have an antioxidant highlighted here in yellow reacting with a peroxide radical, 4 peroxide radicals in this example for low temperature, resulting in a variety of different products. In addition to that, as you are systems are all run at in this case at the same temperature, but in different formulations will act differently at the same temperature, the reaction rates of one oil and another will vary. And the reaction rate is a function of temperature for that reaction. And so you end up looking at this through the Arrhenius equation. So you have a reaction constant and the energy of activation. So why is this important? Because energy activation is kind of what guides whether a reaction goes into one pathway to make product A or to make product B. How this is visualized is through what they're called saddle graphs. So here we have a reactant at the bottom here, and this product can either, reactant can either convert itself into a product A or a product B, depending on the available energy in the system. There's a lot more complexity than just that, but this is just one visual example of how you can end up with one product or a different product due to this different energies of activation for different reactants. So, summary of observed results and interpretation. The reaction chemistry between different lubricants have different end products and rates of consumption. This is consistent with the fact that there is a large variety of additives and base oils in these formulations, various different between the different formulations. In addition, there is a rich literature showing that there is synergistic and antagonistic mechanisms between the additives and oils. And that can also be taking place. And we also know that the reaction chemistries at 120, 180 degrees can follow very different pathways. And this is also consistent with what is known in the literature. As we describe, at low temperature, you have one mechanism. At high temperature, you have other mechanisms forming acids, for example, and not at 120. The solubility characteristics of the overall mixture, and that includes the byproducts of the antioxidants as well as the byproducts of the oils, are very much determine also the delta E value of the MPC. And if those get high enough, then we will find deposit formation forming. So the implications here for formulations and treatments basically are saying antioxidants are very, very effective. They neutralize lots of radicals. They prevent a lot of byproducts from forming, but they're not the only game in town. Neither are solubility improvements alone that are going to control the formation of deposits. Both will be part of strategies for extending the life of fluids. As formulations have changed over the years, the relationship between the consumption of antioxidants and delta E is weaker than it used to be. But however, ruler is a powerful tool in determining the early stages of oxidation. So it will likely continue to be an important measuring tool that in combination with others can be helpful in monitoring the condition of the oil. It's probably best to speak when in terms of end of life, in terms of performance characteristics alone, meaning deposit formation, viscosity, emulsibility, because those are the effects on the actual operations, rather than trying to combine causes and effects in the same at the same level. So this can cause some confusion. But it's not to say that the intrinsic chemical characteristics, such as a ruler, are not to be measured. Quite the opposite. They ought to be measured, but they are serving as monitoring tools rather than defining end of life. One example of a chemical characteristic that it's being used for monitoring is cetan. This is quite old and perhaps needs to be revised. Now, a change on elevation of 0.3 milligrams is very, very conservative. As we saw, there was very little, not much change on acidification when you're already generating lots of deposits. So a much smaller increase, perhaps of less than 0.1, may be a good guideline. Finally, the TAN, RPBOT, and AO are meant to be used as leading indicators. However, we didn't see a strong correlation between them. We noticed that even with the newer formulations, there is an increase in delta E and under accelerated conditions, but it may be worth revisiting the critical level to a lower level of 20, especially with the newer formulations, which may show deposits, but a relatively low MPC. So this lack of strong correlations are hinting that new methods and approaches are necessary for early warning for deposit formation. So this is very much an active area of work. These methods need to be able to also measure transient conditions where the MPC goes up, for example, and then it comes down. So you may miss it. And so sensors may be a path forward to be looking at this type of transients. So I'd like to thank everyone in the operations team and R&D team here at Fluitec who support allow all of this work to be possible and for me to be presenting it to you. Thank you very much.
Hey, thank you, Cristian. Hey, no questions that Yo, kind of summarized it pretty well. He said very clear presentation. So, kind of reiterated one thing that I think is very true. Different types of chemistries react very different to different temperatures. We see that in the field all the time. So anyway, great presentation. Thank you so much, Cristian.
Yeah, you're very welcome.
All right. Bye-bye. Bye. Thank you all.